Good morning or good afternoon, depending on when you're clicking on this video and starting it. Fair warning, this one might be longer than you're used to with the Rock ID videos because this is actually the start of the classroom series, which is, it sounds a little scarier than it actually is, unless, you're into the same kind of nerdy stuff that I am. It's basically just me explaining concepts that I've mentioned in my Rock ID videos, or that I think maybe you guys would like to know about, and kind of exploring them in depth so that then you can kind of understand what I'm going to be showing you later or what I've talked about before. So it's kind of like me playing professor at this point. May as well put my major to good use. Never say that any major is completely useless. No matter what it is, you can probably show it to someone else. Just a little piece of advice from me, because otherwise I would not be using my geology degree at all. So yeah, anyways, all that aside, for this video, I'm going to be talking about igneous rocks because I feel like that's pretty much the starter pack for understanding things that happen later, and also understanding basic things about Earth and stuff like that. Igneous rocks are just like step one in terms of like rock formation, for the most part anyways. Sedimentary rocks are a little complicated. They're not necessarily derived from igneous rocks, but a lot of them can be, but we're not going to get into that until a sedimentary video. So anyways, starting. Oh, also, I am doing something a little different because it's the classroom series. I do have a PowerPoint here. You guys can't see it, obviously, it's off screen, but I'm actually, like, me looking at it, you guys can't see it. Or maybe you can, I don't know. I don't know how wide this view is. But that's not the way you're going to be seeing the PowerPoint presentation. The way you're going to be seeing is that I'm going to have my editor actually put me in a box in the corner discussing certain slides as I reach them. And you're going to be able to see the PowerPoint presentation I put together. So if that's your favorite way of learning, good for you. If it's not your favorite way of learning, then you can just look at my face. As well as you can anyways. I'm also, as the series go on, going to be showing you guys like video clips of whatever I'm talking about, samples of rocks if I happen to have them of specific types, etc. You guys have already seen all the rocks in my collection, but that's like a refresher on, oh, this is what I meant when I said this, this, and this. That sort of thing. Anyway, enough chatter because it's at 58%. I'm probably going to have to change the battery soon, so let's just get it started. And my computer does like to black out literally after 15 seconds, so be aware of that. I will continuously be, that I don't know how to change, honestly. I'm not really a tech person. Anyway, so let's start with igneous rocks then. So yeah. So the lesson, I did actually draw up a lesson plan for what I'm going to be talking about, and I have like certain points here that I'm going to show on the screen now. So basically, I'm just going to be talking about like the composition of igneous rocks. Like, this has a lot to do with the actual elements that go into making up the Earth and like how they're divided up between layers, and I'll get into those details later. I'm also going to be going over the source and origin of all igneous rock formation, like how it actually works, like how do the processes happen to make igneous rocks, that sort of thing. And then I'm going to go through how magma moves through Earth's layers to get exposed. I'm going to move on to different types of igneous bodies, mostly intrusive, because a lot of igneous like rock formations form intrusively. Extrusively, like, and by these terms I will explain what I mean later, but like if the igneous rock body is forming on the outside, it's usually just lava that is cooling, so it doesn't really create like certain big stockpiles of rock like inside cooling does. Just so you guys know, by the way, rocks are not considered lava until they hit the surface. Before they hit the surface, they are just considered magma. Alright? Anyways, after the different types of igneous bodies, the texture of igneous rocks and the connection to cooling speeds, this goes into like classification and IDing. Composition is also somewhere in the, oh yeah, that was the first one. So composition and texture actually determine like how you classify a rock, and that'll be the last slide. Anyway, moving on to the first part, which is composition. So in general, Earth is actually composed of dense material that sinks closer to the core. As the planet is forming, essentially, the gravity kind of pulls the heavier materials obviously towards the core of the cooling planet, And that's why a lot of the, well, I'm not going to talk about planetary geology, that's beyond my, but anyways, the reason that our planet is the way that it is because all the dense stuff stuck, like kind of sunk in, all the lighter stuff floated on top and then solidified closer to the surface in those higher layers. So, and in shallower layers, I should say. So that's how that works. And now, in terms of like what materials I'm talking about that make up all these layers, so I'm just going to go ahead and read off all the elements that are in Earth's like surface and way below. And I'm going to tell you exactly how much of each material is allocated where. You know what I mean? Because we have a lot of the same elements in different layers, but there's like different amounts of them in every layer, if that makes sense. And of course, if anything that I'm explaining to you guys ever doesn't make sense, just ask me and I'll gladly reword it for you. So yeah, there's iron. There's actually 32% of that deeper in the planet. A lot of that sunk in because it's pretty heavy. And there's like 6% of it in the crustal layers, like at the surface or closer to the surface. There's oxygen. There's like 30% of that much deeper in. There's 46% of that in the crust. There's quite a bit of it, like in the ground that you and I see. And then there's like 21% of it in the atmosphere. Anyway, so then there's silicon, which is like 15% deeper, and like 28% of the crust is made up of silica. It's a very abundant material. Actually, silica is one of the main thing in quartz, and as I've mentioned before, there's a lot of quartz in geology. In fact, a lot of the rocks, if not most, I would say, are safely assumed to have some silica in it. And that's why quartz is so abundant. But yeah, anyway. Then there's magnesium. 14% of that is deeper inside. 2% of that is present at the crust. Magnesium is one of those denser materials, as you can tell. There's sulfur, which is like 3% of it is deeper in. It can be exposed through things like geothermal vents, which are in the ocean. And if you want like a really cool little side project, you can just look into that. They're interesting to say the least. And people, kind of like a sidebar comment, when I was in like academia and university, I was aware of the fact that there are certain scientists that are literally studying geothermal vents to see if it is possible that if life forms around there, that could explain how life would form in other planets, even if, say, other planets don't necessarily have living conditions that help life along on the surface. Maybe there's like livable conditions in the ocean or something like that, or even it could exist in hotter areas just because of the venting. So yeah, that's beside the point though. That's just something I think is cool. Then there's nickel, is like 2% deeper. Calcium is like 1.5% deeper and 4% of the crust. There's aluminum, which is 1.4% deeper and 8% of the crust. There's potassium, 2% of the crust. It's only really seen in the crust. It's not seen deeper because it's like easily breakable and it melts really fast. Same thing for like sodium, which is like 2% of the crust. There's nitrogen, that's most of the atmosphere. It's like 78% is nitrogen. I imagine it could be seen in other, like in traces and like rocks, but it tends to be more in the atmosphere. The same thing go for like argon and the other trace gases that make up the atmosphere. Alright, so how does this actually divide up between the Earth's layers? Or like, how do we really talk about the, I would say, the allocation of elements and how they form rocks in the Earth's layers? So first of all, the thing you should know about how we kind of look at Earth and its layers, we look at it in one of two ways. We either look at it like how it behaves physically, like is it more plastic in behavior, is it more ductile, is it more of a solid that's like brittle and rigid so it breaks, or is it more liquid that it flows? That's what we tend to think of when we're talking about like the physical or mechanical layers, as they're called. And then the mechanical, yeah. And the chemical layers are just basically the elements that I just talked to you about, the abundance of each in each layer. So the chemical layers are divided into three: the crust, the mantle, and the core. The inner core and the outer core are both part of the same categorization when you're talking about chemistry, because they have like the inner and outer core have pretty much the same elements. It's just that they behave differently, and that's why they're kind of categorized differently in the mechanical layers. And in terms of like the physical and mechanical layers, before I move on to that, scratch that. The crust is, as you can imagine from what I've been reading from the elements, is largely composed of like silicon, oxygen, aluminum, iron, calcium, sodium. Those are all the rocks that you tend to see there, like all the rock materials, or rather the layers. There are certain rock types that we will probably never see as a species, just so you know, because it is so deep inside. Who knows what kind of cool geology is going on deeper inside? We can make guesses, but without it being exposed to us in some way or other testing that we can do, we're never really going to be sure, I should say. And then of course the mantle is composed of like iron, magnesium, aluminum, silicon, and oxygen in heavier amounts obviously. And the core is mostly iron, nickel, and sulfur. And those are the three elements that are closest to the core. And now, in terms of physical and mechanical layers, like I said, it's physical behavior based. The lithosphere is the crust in the lithospheric mantle, which just means it's like the topmost part of the mantle that behaves a lot like the crust in terms of like being similar tectonically, because it's more like solid up there and it behaves more like with breaking and stuff like that. The asthenosphere is a hot ductile layer of the upper mantle that is still below the rigid lithosphere. I will show you guys, by the way, diagrams of what I'm talking about, so do not panic if this doesn't make sense to you, if you can't visualize it. Also, if you need explanations for what I mean by ductile or plastic behaviors, do let me know. I don't mind answering questions in the comments, but I could also make like a short video explaining it, who knows. Then there's the mesosphere, which is the solid lower layer of the mantle, and is high pressure and very brittle and rigid. So basically, in terms of, the mantle is categorized as one thing in chemical layers, as mentioned, but in terms of like physical behavior, it's the lithospheric mantle, then it becomes the asthenosphere, I have trouble saying that word sometimes, or the mesosphere. Those three make up the mantle. And that's like all the mantle, they just behave differently at different depths. So, and then of course there's the outer core, which is like a fluid layer of molten iron and nickel, and the inner core, which is just solid iron and nickel. And it's solid due to intense pressure, despite the fact that it is so hot in there. Like, generally speaking, if the temperatures are very high, you tend to see melting of rock. That's why the outer core is not solid. But if the pressure is intense enough, then, because that causes more solidifying of materials, generally speaking, if the pressure gets high enough, it does not matter how hot it is, it's going to stay mostly a solid. It might be a little like, it might behave not quite like a solid, like it could fall in the plastic / ductile category, but it's not going to be flowing like a liquid if the pressure is high. And basically that shows you guys the difference. Like, this specific diagram shows you guys a very simplistic rendition of the difference between physical and chemical layers. The physical layering is on the right side, and the chemical layering is on the left side. So you guys can kind of see the difference between how these things are divided up. As you can see, the mantle in the chemical layering is then divided up into 3 different parts in the physical layering before you actually get to, because also some of the mantle is in the lithosphere, remember that. So yeah, now we're going on to slide 6, which shows you the chemical composition. As I've already said, silicon, oxygen, aluminum, iron, calcium, sodium, all in the crust. In the mantle, iron, magnesium, aluminum, silicon, oxygen, and then the 2 different cores. Although those should be 1 if we're looking at chemical, but I'm not going to get too picky about that. And then of course there's the structure. This is going to be on slide 7. This shows you like a really nice, that was just a really cool little diagram that I found. A lot of the layer diagrams that you'll see for geology will show it like pie slices, essentially, where it'll talk about like the different layers, and then you'll see on one side you'll usually see like chemical or physical, and the other side you'll see the opposite. So yeah, that's just a really cool little diagram that I thought you guys might want to see. You can pause the video to look at it if you would like now. Alright, did we get a good eyeful of that? Moving on. Now we're going on to the source and origin of like all igneous rock in terms of like how this stuff actually works. The processes, I should say. Or no, not the processes. That's a future, let me not get ahead of myself. That's a future slide. So, in terms of like the origin, the mantle is largely mafic, because a lot of denser materials are more gathered there than at the crust. So, and in the Earth's crust is largely felsic. because a lot of lighter materials floated on top. So the way that this works is that as there are distinctions, like I'm gonna have to explain the geothermal gradient. Alright, let's see if I can manage to do this. So this is a pretty complex, it's not super difficult to understand. Some people get it right away and some people don't. So don't feel bad if you're in the latter category. The geothermal gradient is basically the rate at which temperature increases as you get deeper into the planet, for simplicity's sake. Different materials have different melting points, which is called the solidus line of that material, due to heat transfer or changes in geothermal gradient. Because the geothermal gradient, it usually behaves a specific way under normal conditions, but it can be moved by different things happening. There's 3 different things that can actually happen to move the gradient. That is the inclusion of volatiles, which basically just means that like it changes the composition of the rock itself, usually due to the addition of water or carbon dioxide. Then there's the increase of temperature, which then causes rocks to be able to melt even if the pressure is not necessarily conducive to it. And then there's depressurization, which then makes the melting point of that rock lower. And I'll show you guys diagrams of what I mean. But basically, the way that igneous rocks actually, like their source I should say, or their origin, is that partial melting in the crust and in the mantle can cause magmas to form and then start rising up and then gather as igneous bodies inside, or they can erupt at the surface and become lava. So yeah, that's how that works. I hope that was a good explanation because I did my best. And actually, like I said, the crust tends to be more felsic, unless we're talking about oceanic crust, because there's 2 different types of continental, of crust. That is, there's continental and there's oceanic. Oceanic crust is, as it sounds, the crust that you see in the ocean, because when you go into the water, you don't just step right into the mantle. That would be a disaster. There is ground underwater and it goes pretty deep in. That's still part of the crust. It's just much thinner along the ocean floor than the crust is like outside of it. Obviously continental crust is extremely thick and very felsic, and because the oceanic crust is so thin, it tends to be made up of more mafic materials. I think I cover that as well later on in this PowerPoint series, but I feel like I should explain that a little bit. So as magmas rise up, they can mix with more felsic materials and make intermediate igneous rocks, or they end up as felsic igneous rocks, or if they kind of mostly stay along the oceanic crust, like if they're over there, or if maybe they just don't gather, who knows, I don't know, maybe it's possible that an igneous rock that's made mostly mafic could come up through the continental crust, but that tends to happen in oceanic crust because it doesn't collect a whole lot of felsic material on its way up, or it doesn't have much distance to travel, so it doesn't get the chance to collect that much. Anyway, sorry, that was kind of a little ramble on the side. So basically, that's all I really wanted to explain, I think, in this case. And like I said, there's 3 different factors of partial melting, which is depressurization, heat-induced, which just means that temperature increases, or flux melting, which is due to the addition of volatiles. Those are the 3 different terms. Oh, and there was something else that I forgot to mention. Certain materials melt faster than others, like felsic materials specifically, so that's why they tend to collect more easily in igneous rocks than like mafic igneous rocks, especially if you're in the continental crust. And it also sometimes can cause a magma body to like become more felsic as it rises. I think I mentioned that as well. And mafic materials are kind of left behind in the chamber to cool underground, while the felsic rocks just keep rising because they're still liquid because they have a lower melting point. So yeah, anyways, now we're going on to slide 9. Let's look at this little lovely diagram. That shows you the geothermal gradient, essentially. You can kind of see how it starts to, as the depth increases, you need increased temperature in order for like material to cross that red solidus line and become liquid. And now moving on to slide number 11, that just shows like different types of environments along the crust where you might see different geothermal gradient behaviors. For example, a normal situation, you know, you'll see like the geothermal radius is pretty far from the solidus line. That's like the first square right there. You would you know, obviously that's just how it looks like normally without anything special happening. In mid-oceanic ridges, the temperature is actually going to be increasing and the pressure is going to be decreasing because, you know, it's breaking through at a shorter amount of time. The rocks are getting hotter despite the fact that they're so shallow, etc. So then you see the solidus line move over and you start to see melt there, and that's how mafic igneous rocks tend to be formed. Hotspots are also a case of like, this shows decompression versus flux-induced melting. Remember, decompression, lowering of pressure, so then the temperature kind of can have more of a play than, and you don't have to worry about it not being the proper pressure for melting. And flux-induced melting is just because you added a volatile, in this case it's a water, and that changes the shape of the melting curve, so then the wet mantle rock begins to melt a lot shallower than it would have to be in order to melt normally. And then of course dry, or as I should say, it starts to melt a lot deeper, I should say, than it would normally. That was a misspeak on my part. Of course, in terms of decompression melting, as pressure kind of starts to lower because of tectonic activity, usually the dry mantle rock begins to melt like faster as the crust thins thanks to tectonic activity, so it can melt in shallower depths. You know. Anyway, I hope I explained that properly. If not, you guys can spend extra time looking at these graphs. You can look it up yourself if you're curious. You can ask for another video for me to explain it better. Now that we're done with that, we're gonna actually go into how do magma bodies actually form? Like, how does this work? How does it move once they're formed? So the two main methods of like magma rising are buoyancy and gas expansion. In terms of buoyancy, as the magma is actually hotter than the surrounding material, it's going to rise because liquids tend to rise over solids. It's just how it works. The lighter material is, the higher up it wants to go because it floats on the denser material. I think everyone pretty much knows this elementary concept. I don't know why I'm over explaining it. But yeah, so that's how buoyancy works in terms of magma. It works with magma too, is what I'm telling you. And gas expansion actually helps accelerate this because pressure starts to decrease, gases start to escape, and that makes the material even less dense, so then it keeps rising. And also that's when you tend to see like some volatility in terms of like gas exploding out of chambers depending on how fast it's depressurizing. That's why some volcanoes are more explosive than others, because the rising is a lot faster, so the depressurization happens more explosively, and you see all kinds of cool stuff. Also really scary stuff. I would recommend staying away from areas where there's more explosive volcanoes, because if that baby ever erupts, that's all I have to say. Alright, it's not necessarily the lava that's going to kill you. I'm just saying. Magma can either breach the surface as lava, or it can never breach the surface and instead be stored and cooled underground. And as magma moves upwards, depending on where it's headed, like whether it's headed through continental or oceanic mix, that's where I was talking about earlier. As magma rises, depending on which kind of crust it's rising through, it can mix with more mafic material or felsic material, creating mafic igneous rocks or intermediate / felsic igneous rocks. Mafic materials, as I said, are denser than felsic. So yeah, I'm just going to show you guys this cool little picture on slide 3. That's one of the ways that you can actually, that's the primary way that you see lava at the surface, or magma at the surface, which is now called lava. Cool little volcano pic. I just wanted an excuse to put a picture of a volcano. Anyway, I really like volcanoes. I don't know if you guys can tell. I don't know why I didn't end up studying them. I guess I just didn't feel like it. Now, in terms of igneous bodies, like the big collection and storage of igneous rocks, there's different types, and it also depends on where cooling actually occurs. Extrusive rocks are those that form when cooling occurs above ground, which means it happens quickly because it's exposed to the air and or water. Magma has now become lava at this point. The intrusive rocks occur when cooling happens below the ground slowly, and there's a lot of ways for them to be stored underground. Like I said, there's many ways for them to be contained below ground. Let me just gather my thoughts. You're actually gonna see in this slide, like, the top of the square, this is also something I used to see a lot in geology classes, where they have like little cubes of where they show you like, oh my goodness, cross sections of the planet, essentially. It, like, theoretically how we expect, you know what I mean, especially if we're explaining a concept. These also are done a lot in sedimentology to show the types of sediment seen in different environments. If you want me to get into that in a future video, I definitely can. It wasn't like my best subject, but it was okay. It was interesting enough that I kind of know it well enough to explain it. Though I can't promise anything. I didn't go into sedimentology. I was actually going to study earthquakes, just so you guys know. But yeah, anyway, so back to the little diagram. This little box diagram. The extrusive or volcanic rocks that cool quickly at the surface, you kind of see are at the top. Doesn't, like, there's not a lot to it. There's volcanoes, there's lava. You know, that's how that stuff happens at the surface. Now, the intrusive or plutonic rocks are those that cool slowly, like below the ground, obviously. There's a lot of different types. So yeah, there's different types. There's like, there are stalks, which once fed active volcanoes. They cut directly across surrounding country rock, as you can see. And like, country rock is just pre-existing rock that was already there before there was a magmatic intrusion. So it's just like the normal rock that's already there. And it can cause contact metamorphism, which I'll get into in another video. That's one of the ways that that occurs. So yeah, that used to feed a volcano. That's really cool. It doesn't, obviously, anymore. Apparently the one in this diagram used to feed a very big volcano. That's scary. And then there's dikes and sills. They're just more column-like intrusions of magma that cut into pre-existing rocks before solidifying. Either vertically, which is what a dike is just like a vertical column is going up, cutting across. And then there's a sill, which cuts parallel to the layers of rock. So it kind of lays down gently along the layering rather than cutting straight through it. And then, of course, there's pipes, which are cone-shaped bodies of magma that tend to feed active volcanoes. So they're what a stalk used to be, although this pipe is very thin in comparison to the other one. But you can see a few dikes and sills and like stalks here. I think there's only one stalk in this photo, actually. Now, the other two are called laccoliths and batholiths. So basically, they're both larger bodies of magma that cause like cool formations if they're exposed to the surface by tectonic activity, because they tend to be massive. Okay, laccoliths are more like dome or mushroom shaped, and they basically are caused by like the rocks that are kind of there existing. As magma pushes up and like starts to cool, it causes the layers of rock to start bulging upward, and that's what creates the dome or mushroom like shape. As you can see in the diagram, there's one. And then there's batholith, which is like just really massive and can expand over large areas in terms of like distance. It can cover a lot of distance, okay? It can cover more than 100 kilometers squared. That's a lot. It's a lot of distance. But anyways, you can see that batholith looks massive in that diagram, and that probably stretches for so long. Alright? Anyway, something else you might see are called xenoliths, because you'll see it there in this diagram as well. That's just like country rock or surrounding rock that has fallen into magma bodies as it's intruded upon. Like maybe it's created a chamber of magma, and as the magma continues to like heat up and melt the rocks above it, those little pieces fall in and then solidify inside the magma. Sometimes you see this when you're looking at like rocks and you see something that obviously doesn't belong there and it doesn't make sense as part of the rest of the rock because it looks out of place. That might be a xenolith. Now, moving on to slide 16, because we're moving on to the texture of igneous rocks now. So, with everything that I've explained so far, the texture will hopefully make more sense to you. You guys should already understand how composition works because of what I've explained, like, you know, all the elements that make up the composition of rocks and why you see certain rocks come more, like, commonly in specific types of crust, etc. No, in terms of texture, that has to do with the cooling speed and processes. That's the second thing that determines a rock's ideal composition and texture. So there's like, I would say there's around 7 different texture classifications that I'm gonna go over. And they're the only ones that I'm aware of. If there's other texture classifications, do feel free to drop it down below. Because I'm always interested in learning something new too. Who knows, maybe certain things have changed since I finished school, or certain things that I wasn't aware of were already known to others. So there's like the 2 classifications, or rather the 3 classifications that you immediately think of. or that most geologists immediately think of, that is, are phaneritic, which is coarse-grained rocks, and that just means that like the cooling was done slowly underground, so the crystals actually had time to form specific shapes and can be seen. They're visible. You can see the crystal grains distinguished from each other with your naked eye. You don't need like a microscope or like a lens or anything to see the grains distinguished from each other. Aphanitic is the opposite. Those are fine-grained rocks that you cannot see the individual crystal grains because they cooled so quickly that they didn't have time to really form big grains. And then there's porphyritic rocks, which are just like a mix of the two. Two-stage cooling occurred here at some point. So basically, at first, the rocks cooled slowly below the ground, like parts of the magma got to cool first underground, and it happened pretty slow. Then probably because of tectonic activity, volcanic activity, those are connected by the way, or like anything else, etc., the rocks rose to the surface and finished, like the magma rose to the surface and finished cooling above ground. And so what you'll basically see is like two different rock grain sizes. You'll see visible grains and kind of like a uniform background. That uniform background is made up of tons of little crystal grains that you can't see because they cooled quickly. That's the part that cooled after it came above the ground. And the big grains you can see, those are called phenocrysts. The parts you cannot distinguish are called the ground mass. And then of course there's glassy or vitreous rocks, which is like your obsidian. Basically it's smooth and shiny, and it's formed due to instant cooling upon contact with water or air. It happens so quickly. Like, the cooling happened so fast that the crystals did not even have time to form. They're just there. Like, the elements are there, no crystal grains have formed. What you're looking at is just really smooth and shiny. It's really cool. I don't know how effective obsidian knives actually would be for more than one use, though. So, because I know that there's a lot of enthusiasm about obsidian knives. They look really neat. They probably don't last that long. I don't think you guys understand how brittle this stuff actually is. You can stab someone with them once, and then it's probably going to break on you. I'm not telling you to stab anyone, by the way. Do not take this as permission. Then there's vesicular rocks, which is like rocks pockmarked by cavities. Like, they kind of look like sponges, and they're caused due to dissolved gases bubbling up out of the magma body as lava depressurizes and cools. So like basically as the magma starts to cool, pressurization basically starts to release, like pressure starts to release on the rock, and so gases that are trapped in there can escape, and they leave behind holes, like they punch their way out. And it's really cool. Like, it's scoria, pumice. I've shown you guys some samples of that, and I'll probably show you guys again at the end of this video. And then there's pegmatitic, which is very coarse grained, with potentially massive crystals that could be as many as meters long. It tends to form in like later stages of cooling of a magma body, especially if water is present, because a large amount of water can move around the ions, which is very atomic based type. It's very atomic conversation that I don't want to get into now, but if you know what ions are, then congrats, you probably understand this part better than those who don't. Basically ions are just like different charges. Alright everyone, I am back. My camera, as predicted, turned off. That's what happens when you don't fill it with a full battery. The funny thing is, the other battery I picked up is at even less percentage than the last one that I started out with, so let's try to make this quick. Alright, so, that's why I'm going to leave it for now, because the battery is getting dangerously low.